Recording. Okay, guys. Do you guys have any questions? Okay, so last time we did the graphing, okay, of all of these functions. Okay, and you've done homework, right? So this is the one of the curves, one set of curves. And we have also done the shifting, right? We did this one. Okay. Let's see, did we do the horizontal shift? I don't think we finished that, did we? Okay, let's see. Let me just make sure. I think we did that, didn't we? There. Okay. So we did all three sets. Okay. So what have we learned from here? What have we learned from here? Percent there. So we have learned something from this process, didn't we? Okay, I can see Cortland. Let's see. I still cannot. I can see you guys if you turn on the camera, but I cannot turn on my camera. Okay, but that's okay. I'm sorry, guys. I don't know what happened. Okay, so we have these. We have graphed all of these functions. So we've done some groundwork, and we have done some observations as well. Right, we've done some observations. So let's summarize the features we have observed from these graph. Any issues with the quiz? No? No? Okay. Now, from these pictures, right? Some of these are even functions, right? For quadratic, and some of them are not. Therefore, we cannot keep this. We cannot keep this feature because not every quadratic function is even function, right? So we're going to remove that. Does everybody follow me? It is no longer an even function. Okay, it has domains. It has range. Okay. And it's symmetrical with respect to something that varies. And it has vertex that varies. Okay, the vertex is not always 0, 0. As far as minimum, maximum, it varies. Okay, so I'm going to add one more row here. So this way, we're going to put all of these feature considerations in one column, Okay, and line of symmetry. Okay, so we're going to put line of symmetry that varies. Line of symmetry varies. Line of symmetry varies. Okay, so by this time, so we have all of these features summarized. Okay, so let me bring this to the top. And that's a a summary about quadratic functions that we have done. Okay, the quadratic functions we have done. Okay, and do we have other features? It's not a one-to-one domain. Domains seem to be all the same for all of them. Okay, and the range varies, right? Range varies. Line of symmetry, vertex varies. Now, I want to add a couple more questions. Intercepts. Okay, intercepts. I'm gonna put it here. Okay, intercepts. Insert. I'm gonna make it 2 rows. Y-intercept. X-intercept. Okay. Do we have y-intercepts for all of them so far? Do we understand what is y-intercept? Where the curve crosses y-axis, right? Where the curve crosses the y-axis. So do we have y-intercept for all of them? We do, right? We do. For example, for all of these curves, the y-intercept is right here. 0, 0, right? How about the y-intercept for all of these? The 3 in the middle, they all have y-intercept. Obviously, they're not at the same place, right? So it varies. Y-intercept varies. Varies. Carries. Okay. How about x-intercept? X-intercept. Where do they intersect with the x-axis? Well, that varies as well, right? That varies as well. So for these 4 curves, x-intercept is the same as y-intercept. But on these, they are different. Okay, these are x-intercepts. And it's interesting to point out that in the middle, okay, this green, this green has no x-intercept. Did you guys notice? All of these have x-intercepts. These have x-intercepts. These, the red here has x-intercept, but the green has no x-intercepts. Okay, and all 3 here on this picture, it has x-intercepts, but they all vary. Sometimes you have, sometimes you don't. Do we always have y-intercept? That's the question. Do we always have y-intercept? The answer is yes. Okay. Do we always have x-intercept? The answer varies. Okay. varies. Sometimes none. Okay, so we may have x-intercepts and we may not have x-intercepts. So varies. Okay, varies. Sometimes none. Okay, sometimes none. And so we always have x, we always have y-intercept. We always have one. But x-intercepts, however, in these cases, okay, in these cases, look, green touches x once, okay, x squared touches x once, half x squared touches x once, 2 times x squared touches once, negative x squared touches once. That has only one x-intercept. So sometimes we have one x-intercept. And in this picture in the middle, the red touches x-axis twice. Sometimes we may have 2 x-intercepts, right? And the green, we have none, no x-intercepts. And in these 3 cases, 1, 2, 3, okay, in these 3 cases, we have how many x-intercept? Exactly 1. So we have 3 cases already, okay? So sometime we may have none, okay? 3 cases. Okay, so let's summarize it here. So far, 3 cases. We may have 2 x-intercepts. We have 1 x-intercept, and we have no x-intercepts. 3 cases. That's what we have observed so far. Okay, so these are the observations about quadratic functions. In the how many cases have we considered? Right, how many cases have we considered? Let's count. How many cases? And this has 4 cases, right? 5, 6, 7, 8. In 8 cases. 8 cases. Okay, the x squared was done, repetitively. 8 cases. Now, it's time to consider this general form. Remember we talked about this general form, which is ax squared plus bx plus c, where a is not 0. A is not 0. Okay. One of the questions is that how do we study this? How do we get the picture? Okay, how do we get these pictures? Okay, so I'm just making it a little bit larger on the fonts. It turned out that this is a class. Okay, this is a school. Okay, this is a class or school of functions with common features. With the common features. And what are these common features? The common features are all listed in this table. Okay, they're all listed in this table. Okay, I think we pretty much have them all. We pretty much have them all. Now the question is, for specific ones, how do we graph them? For example, right? Last week, last Thursday, we have a couple functions that we may not have a graph. For example, this one. Okay, so let's this guy, x squared plus 2x plus 1. Right? Did we graph this one? Did we graph these two?
I don't think so.
Oh, sorry. Have we graphed these two? The answer is we have. We've done it. Why? Because if you factor x squared plus 2x, it is equals to x plus 1 squared. If you factor the latter one, that. So we have graphed them. They were just in disguise. So we have graphed them. And this brings an interesting aspect, right? So for any quadratic function, if we cannot, well, can we make them all perfect square? These are called perfect square. Can we make them all perfect square? Because if we can, we know how to graph them, right? We know how to graph them. For example, right? So these are perfect square. Could we, okay, so my question is, you see, we have graphed the perfect square cases, right? These three cases, right? Now the question is, could we make perfect square? Okay, perfect squares for every, okay, could we make a perfect square for every quadratic function? Do you guys know what's perfect square? Do we know what's perfect square? Does everybody know what's a perfect square? In basic 8, I don't know if you guys paid attention to basic 8. There are some perfect squares out there as a review for elementary algebra. We didn't spend much time there. I don't know if you guys paid attention to it. Okay, so to answer that question, we need to know what is a perfect square. Okay. Can anybody tell me what is a perfect square? For example, 1 is a perfect square because 1 is equals to 1 squared. 4 is a perfect square because a 4 can be written as 2 squared. Do you understand what's a perfect square now? 9 is a perfect square because 9 is 3 squared. So anything can be written as an integer squared. That's a perfect square. That's called a perfect square. Okay. Then you say, how about decimal fractions? Fractions, yes. Decimal, yes. Okay. For example, a quarter is a perfect square because a quarter is a 1/2 squared. All of these are examples of perfect square. 2.25 is a perfect square because it is 1.5 squared. Okay, so these are examples of a perfect square. Okay, then but these are just one number, right? A single number as a perfect square. How about these cases? Okay, how about sum of numbers? How about a sum as a perfect square? Or differences as a perfect square? So in generalization, this is a perfect square, right? These are perfect square too. True. And of course, then you say, well, how about three numbers? How about we do, wait, how about we do A plus B plus C? Of course, you can keep the list going on, right? You certainly can. But we're not studying those cases. Right now, we're studying these two cases. Okay, those other cases will be more complicated. Of course, you can do it. But you see, mathematics, we typically do from simple to more complicated, right? We always start from simple, and then we gradually get to be more complicated. All right, so let's look at these two cases. Right? And we should be fairly familiar with these cases, right? We learned this in elementary algebra. So what is it? How does it look like? Do you know how to FOIL? Could you FOIL them? Could we FOIL them? Could you FOIL them, please? Does everybody know what is a FOIL? Does everybody know what is a FOIL? Yes? The first with first, that's F. Okay? The first with first. That's A times A. Okay. O, okay, outside, A with A with B, okay, the outside, the two outside. So that's A times B, okay? And this is outside. And next one, I, right? The third letter I, insides. So that's B times A. B times A. Okay, so this is the I. Okay, last in each parentheses. So that's B times B. That's a FOIL. Does everybody follow? If you have forgotten FOIL, okay, practice FOIL in basic 8 for those perfect squares. Okay. And go find an elementary algebra and to do some more FOIL. Okay, that's elementary algebra material. That's okay. So you can find any elementary algebra textbook and you might be able to find some exercise in pre-calculus. And practice, very, very basic skill, very, very basic skill. Okay, FOIL. Now, then we're just going to be, now we get A squared, A times A is A squared. And we have AB plus BA. A times B is the same as B times A, right? So that's 2AB and plus B squared. These two formula are very, very often used. Even though you're learning elementary algebra, you probably have used it along the way, and you will continue to use them sometimes in calculus classes. So it's really one of those academic formula you're going to be used very often. So by the same similar steps, you get A squared minus 2AB plus B squared. So that's what FOIL give us. Now, to summarize, right? If we put these two side by side, right? We put these two side by side. Okay, side by side. Okay, and we'll look at what's in common between these two perfect squares. These two are perfect squares. Can you say the word perfect squares? Perfect squares. If you see the right, you need to be reflected on this left, because we often go from left to right, right to left. Okay, so now look at the one we just considered. We just had. That's an example of the right, which is the same as left. And you need to identify what is A, what is B, and what is that? Is it perfect square? So how do you identify if there's a possibility that's a perfect square? Can you identify this is what kind of perfect square this is? Can you identify if this is possible to be a perfect square? Well, in this case, if it is a perfect square, you will have a perfect square here, plus another perfect square here. And in the middle, it has to have some special features. Do you guys see that? Okay. Observe it carefully. Because the next thing we're going to talk about is identifying perfect square. Right? Oftentimes, you might be given something like this. And will they give you something like this exactly? Of course not. They're going to show in different kind of shapes and forms. And we are to identify whether it is a perfect square. If it is yes, you need to know what is that perfect square. If it's not, and the question is, how do I make it? How do I make one, right? So these are the topics we're gonna do, in this section as well. Then you say, well, do I have to do this? Yes. That's another academic, techniques. Is it useful in practical applications? I don't know, maybe, I don't know, depends on what you're gonna do as your career. But if you have chosen STEM, and you've chosen you're gonna go through the calculus track, and then you have to get over this academic hurdle. And it's not that difficult. So I'm gonna show you the way. I'm gonna show you the way. Now, first of all, you have to identify there are possibility to be perfect square. And you realize, oh, x squared is a perfect square. And x squared and a squared, they seem to be a correspondence. And 1 is the same as 1 squared. So maybe 1 squared and b squared are correspondence. And the next thing you need to check, of course, this needs to be plus b squared, because in both formula you have plus b squared, right? Even if it's adding, this is a plus. If it's subtracting, this is still plus. Do you guys follow me? Now the question is, the middle part has to be 2ab. The middle part has to be 2ab. So if a is x, b is 1, 2ab is exactly 2x. And we have a plus 2x here. Therefore, and we would imagine this might be x plus 1 squared. This might be x plus 1 squared. And of course, you have to verify. Of course, you have to verify. Do you guys follow me? And this letter 1, the same thing. Right? This letter 1 is the same thing. Okay? This is a perfect square. And then we plus another perfect square. 1 is the same as 1 squared. And in the middle is 2ab if a is x, b is 1. So we have this perfect match. You guys see that? So therefore, we get another perfect square. And we got it easy this time. We got it easy this time. Sometimes it's not that easy. Sometimes it's not that easy. Okay, so how do we identify these perfect squares? Basic 8. Okay. Could you guys turn to basic 8? Did you guys do them? Then you should do it again. Okay. We start to find some patterns about these perfect squares, don't we? Okay. So I'm going to put these two formula, I'm going to combine these two formula in one. Okay. So this is a plus minus, and that's a plus minus. And this is the way that when I was a student, and by combining this into combine 2 into 1, it makes it a little bit easier to memorize. Okay, so of course, memorizing this formula is really not a big deal because you're going to memorize it very quickly. The important part is how to identify whether it's a perfect square. So we're going to do identifying perfect squares. Okay, so with that in mind, okay, we're going to identify some more perfect square. So I'm going to give you some examples. Okay, I'm going to give you some examples. Are you ready? You are to identify perfect squares. X squared Okay, just 3 of them. Are they perfect squares? If they are, what are they? You can use basic 8, the second table in basic 8, as your reference to identify these perfect squares. If they are, okay. The first question is it a perfect square? Secondly, if it is a perfect square, make that perfect square. Okay.
Is the first one x plus 2 as the power of 2?
So x
parentheses
plus
x plus 2
squared.
to the power of 2.
Very good. You can verify this, right?
Yeah.
Is it perfect squares? Is it a perfect square? Perfect. Oh, perfect square. If yes, how does it work? How does the perfect square look like?
And then the second one is parentheses x minus 2 to the power of 2.
Very good. Excellent. The last one.
It's not a perfect square.
Why? Okay. You're right. Because you see -4, right? It
Yep.
has to be a perfect square plus another perfect square. If you have a minus, it will never make it. Okay? All right? It's not a perfect square. Not a perfect square. Okay, let's do some more. Okay, I'm going to give you another set. Another 3. Okay.
The first one's x minus 3 to the power of 2.
This one?
Yeah.
Are you sure?
Yeah.
Wrong.
Oh no, that'd be positive. No, never mind.
That's right.
Never mind. That's wrong. Yeah, there's none.
That's right. Very good. So how do you quickly recognize it is or it is not? You should have 2 positive perfect square. You guys see that?
Uh-huh.
If that's not, it's not. Do you follow me?
Got it.
Yeah. So this one, just like x squared minus x minus 4. Okay, so this is not a perfect square. Okay, so I'm gonna give you one more set. Okay, these 2, are they perfect squares?
Yes.
So what is the first one? X squared plus
X
14.
x plus 7.
Sorry.
I mean negative 7. Oh wait, no, that's positive. Never mind. Plus 7. Yeah. X plus 7. The power of 2.
Perfect. Good job. This one?
X minus 5 to the power of 2.
Wonderful. Now keep going.
Okay. So you remove that 4, and then that's x plus. Oh, there you go.
For that one, is it parentheses 2x plus 3y squared?
That's wonderful. 2x plus 3y squared. Good job. It is a perfect square, right? Good job. Next one, x squared minus x plus a quarter.
Is it x minus 1/2 squared?
That's right. Very good. So can you share with us how you get it? You start to develop your own way to identify it, right? Yes?
Yeah.
Yeah. Now, the last one. And I promise you, this is going to be the last one in this group of exercise. Okay, but we do have more. We have other exercises coming up.
Parentheses x plus 1 to the power of 2.
X plus 1 power 2.
Yeah.
Did you verify that? I think we did x plus 1 square somewhere. Does it match this one? So if you FOIL the right, do you get the left? Yeah? Does it work?
You wouldn't, no,
No, it doesn't work.
you would get 2x.
That's right.
Yeah.
Right? It doesn't work. Doesn't work. So is it a perfect square?
No,
It's not. It's not. So from these examples, what can we conclude? Let's see. I'm sorry, I'm missing you guys on the chat. Okay, okay. All right, now I start seeing it. Sorry about that, guys. Thank you for your contribution, Mikhail and Cortland on chat. Yes, okay. All right. So what conclusion can we draw about my earlier question? Okay, what was my earlier question? Hold on. What was my earlier question? My earlier question, could we make a perfect square out of every quadratic function? Could we make perfect square out of every quadratic function? This is not, right? This is not a perfect square. So let me put it here. Okay. Is this a quadratic function? Certainly, right? If we judge by this quadratic function, the general form, which is ax squared plus bx plus c, where a is not 0, right? If we judge by that, when a equals to 1, right? Hold on. Did I make capital? A is 1, B is 1, C is 1. And what do we get? We get this quadratic function. It's a very simple quadratic function. But it's not a perfect square. It's not a perfect square. But we have seen other quadratic functions, and this guy is a perfect square, and these are perfect square. So what can we say about this question? Can we make a perfect square for every quadratic function? What is the answer?
No.
Nope. The answer is no. The answer is no. So what does that mean? It means sometimes we can, and sometimes we cannot. Sometimes we can, and sometimes we cannot. Now, new question, okay? Can we always, okay, so I'm gonna change the question. Okay, instead of asking, we know that the answer is no. Can we make a perfect square for every quadratic function? The answer is no. Can we make, okay, a perfect square for part of a quadratic function?
yes.
That's right. Very good. And that's what we're going to do. Okay, that's what we're going to do. So we're going to start with simple. We start with something simple. So yes, we cannot make a perfect square out of every quadratic function, but maybe we can make a part of it a perfect square. Okay, and we are going to do that. So the answer is yes. Okay, so now, for example, right? Suppose, okay, I have x squared plus 2x minus 3. This obviously, this is not a perfect square, okay? Not a perfect square. Could we make a perfect square for part of it? And you just said no, we just said yes. And now the question is, how do we make it? The answer is yes. The next question is how? To answer the how, we need to look at the second table in basic 8 again. Do you guys follow me? Do you guys follow me? Do you look at, are you looking at the second table or basic 8? Part of it. Part of it. Right? We have the x squared. We have the 2x. If we add 1, subtract 1, and subtract 3, then you say, well, we add 1, we make a perfect square. Why do we subtract 1? Subtract 1 because we want to keep them the same, right? Anything at 0 stay the same, yeah? So we practically added 0. We practically added a 0. But we still want to maintain that sameness. Okay, we still want to maintain that sameness. Okay, so the latter is still the same as the previous. In order to do that, because in this matter, we take care of 2 things. One is making that perfect square, and second is maintain that equal sign. So the latter is still the same as the previous. By making this perfect square, right? And we are able to get x plus 1 squared. And minus 1, minus 3, that turn into minus 4. Does everybody follow me?
Yep, got you.
Does that make sense?
Yes, a lot.
All right. The next question is, can we make a perfect square out of every, can we make a perfect square out of every out of part of every quadratic function? The answer is yes. And the rest is just technique. The rest is just technique, right? Because we acknowledge we can. We acknowledge we can. Okay. Do you guys think you can do this? Totally, right? And this process is called making a perfect square. Okay, so the typical scenario, the typical scenario is you have a squared plus bx, okay? The typical scenario is this, right? We have this function. Okay, so we're gonna make a perfect square on this part. Along the way, we're gonna add or subtract. Okay, we want to keep the sameness. So we want to make a perfect square and also maintain the sameness by adding 0. So typically adding 0 is commonly used. And then we make the perfect square. So let's look at some examples, okay? So let's start making perfect square, okay? Let's start making perfect square. Are you guys ready to try a few?
Yep.
Let's go. I'm excited to hear that. Resounding, yep. Okay, so next, I'm gonna give you, okay, is x squared minus 2x plus 3.
Okay, so that's not a perfect square, so we can add 4. So we can add. Oh, you can add a 1 to the first one, so x squared minus 1 to the power 2 plus 3.
Do you want to, do you guys want to show me some work? I'm gonna give you just these 3 questions. Can you, would you like to show me some work?
So
I
the first
can-
one, the first one, yeah,
Mhm.
you could get x minus 1
Mhm.
parentheses, and then you would get what's it called 4 on the outside.
Do what?
Wait, no, you know, my bad. You get about 2 on the outside. Yeah, plus 2.
Minus 2
Plus 2.
plus 2. Does everybody agree? How do we check the answer?
Foil.
That's right. Foil. You just have to foil to see if you go back where you came from, right?
Uh-huh.
All right. How about the next one? Good job. Excellent. Okay. Now I'm looking at the chat, or if you want to contribute, you can send a picture. You can send a picture. And the other thing I'm going to ask you that, did you guys find some patterns?
Yeah.
Yeah, can anybody share with us what pattern have you found?
The one in the middle has to equal to 1 times the third one.
Can you write it down on the chat? We take our pattern finding very seriously, right? If we find a pattern and we realize that's a pattern that works, and that's a precious summary, right? That's a precious summary. When you start to write it down, you start to really think about it very carefully.
Can I answer the next one?
Mhm.
So for x squared minus 4x minus 5, the partial quadratic, well, not the partial quadratic, but the answer should be x minus 2 squared minus 9.
X minus 2 squared minus 9. Okay, we're gonna verify. Did you check it, Cortland?
I did not check it.
Okay, could you show some steps for us?
I can. Do you want me to say them out loud?
Yeah, go
Well,
ahead.
the first,
Yeah.
Well,
So it's x squared minus 4x
minus 4x, and then it should be plus 4.
plus 4.
And then yeah, I just got my answer, but I cannot explain how I got there.
You did it in your head, right?
Yeah, I did it in my head.
Good. Well, that's very smart, but that's I think I would
well, if you
subtract
could just
4
FOIL it.
and minus 5. You got the right answer.
Yeah, that's the right answer.
Right. So very good, you guys. I think you got the hang of it. I just need to challenge you guys a bit more. Okay, so that's my -9. Your answer is absolutely right. Okay, so what you do, you just add a 0. You add a 0, and this 0 is your choice. How do you make that 0? You do +4 -4. That's a 0. That's maintain that equal sign. And then you get a perfect square, and then you have a minus number, or sometimes it could be a plus a number, right? So now the last one.
I'm gonna answer it.
Sure.
Okay.
What do you do?
Well, first you're gonna remove the negative
How do I remove the negative?
by putting in parentheses and then putting -1 on the outside.
Okay, so x squared
And then -1.
minus 1
Well, no, +1. My bad. Yeah, because you
plus
just do that.
plus 1. Is that what you meant?
That would give you the wrong answer once you FOIL it. But I think that's right. It's the power 2.
They don't look the same.
Yeah, let me FOIL it just to make sure.
Everybody put on your thinking cap, okay? Everybody, please put on your thinking cap.
Oh. Oh, that's right. I fucked up. Then you remove it now. You have to change all the signs.
So you factor the negative sign.
Then you have to remove all the negatives. All the negatives out. So you change all the signs.
So you mean, do you mean this?
Yeah.
All right. And you want to double check if you get it right, right? You're gonna, go one step further. You want to go one step back, right?
Yeah.
And then what?
-1. Then you make it a perfect square. So you make this one -2.
Is that a perfect square? Is the inside a perfect square?
No.
No. So what do you do to make it one?
You add a number to it.
You add what to it?
You can add, I would say 1, but yeah, you could add. Let me check.
You are getting there.
It's 1, right? But
Are you sure? You're very close.
Can you just leave it like that?
Well, you haven't completed.
it's not a perfect square.
You haven't had a perfect square.
Oh, you just add 1.
That's right. You add 1
And then minus
minus
1.
1, right? You add 1,
then
you have to
minus 1.
subtract 1 because you have to maintain that equal sign, right?
Yeah.
And then what?
And then you add those two together, the negative ones on the outside. So -2 on the
So
outside.
these 3 make
and
the
then you
perfect
perfect
square, right?
Yeah. So then
So
the
x minus 1 squared.
yeah. -1, and then the outside would be times -2.
Okay. So here, I want you guys to put a bracket. Okay, not yet. Okay, did you say -2 here?
Yeah.
-2.
-2.
Could you verify?
Yeah.
When you
Okay.
verify, do you go back where you came from? Did you?
I got something completely different when I verified.
Something is off, right?
Yeah.
So we have to be very careful. We have to be very careful. So what I would suggest is I'm going to put this in bracket and put these in parentheses. Okay. And insert one more step. Okay. So what we have here, that this piece is already a perfect square, which is x minus 1 squared. Okay. Inside the bracket, this is a -2. And next, I'm going to apply the negative sign to each term inside the parentheses. So I will have a negative of x minus 1 squared, and over here should be a +2. Do you follow me? So now you got how to do it, and then you have to attend these little algebraic details. You get it? In other words, we have to be very, very careful in the steps.
So final step, you distribute the negative. That's all we were missing.
I'm sorry?
So the final step is just to distribute the negative.
That's right. You distribute this negative to the parentheses, and you distribute the negative to the -2. That's how we get a +2. So this -2, that's where the problem is.
Got it.
Okay. So when we do something like this, when we factor everything out of the entire parenthesis, entire expression, we need to express it properly. Okay. And at this step, you may want to check already. Okay. Check. Okay, you've done a great job doing this. However, there are there's a minor thing that we missed, right? But that has to be made correct. So every step of the way, you need to check, right? So here, I'm going to check, I'm going to apply the negative sign to each one inside the parentheses, and I want to make sure I can go back here. And then I will proceed. Now I proceed with this parentheses, but because I'm going to add and subtract and stuff, so I'm going to use a bracket. Okay, so I'm adding a 1, subtracting a 1, right? Adding 1, subtracting 1, and then regrouping. And we get a -2 here. And this -2, after we apply the negative sign, it's going to turn into a +2. And now if you verify, so just remember, always verify, okay, on your scratch paper. Most of the cases, you're verifying this on your scratch paper. Okay, and you have to go back exactly where you started. Are you guys verifying? It may seem tedious, but this step is very crucial. So you verified this one, this guy, okay? You don't get back. You verify this guy, you got back. You follow me? So this one is just a little bit off. It's off. The devil is in the details, right? Okay. I think we're ready to move forward. So now,
Forward.
what pattern have we found? Do you think the second table in basic 8 is helpful sometimes? What pattern did we find there? What pattern did we find there? Hmm? We can recognize if it is a perfect square, it's not a perfect square. And we even know how to make some of those perfect squares. But what does the pattern in the second table, basic 8, tell us? Hmm? Wait, okay. I think the order. Oh, wait, I think I might have referred to the wrong table. Okay, quadratic 3. Quadratic 3, I'm sorry. Okay, quadratic 3. On your, in the note, quadratic 3, my bad. Okay, so I'm gonna bring up this table here just to make sure we are on the same page. Okay, I'm gonna share with you. This is the table I refer to, quadratic 3. My bad, I was using the older version of my notes. And of course, this is a new one. What pattern did we find here on quadratic 3? For these series, these are the perfect square you use very often. But of course, the perfect square are not limited to them. They're not limited to them, okay? But if you have something, if you have x squared, right? And you have 4x. And you add what?
4.
You add a 4. And 4 is half of 4 here squared. Did you guys see that?
Yep.
And the 9 is half of 6 squared.
Yep.
16 is half of 8 squared.
Oh, they all
And
are.
it's the same on the other side. That's the
Wow.
pattern I refer to. And of course, you can see a lot of patterns, but this pattern is one of those very important ones. Okay, so do you think we're ready to move forward?
Yes.
Right. Okay, so I'm going to stop this share. And I'm going to put this away. And I'm going to bring you back to this screen. And now we're going to do some serious work about quadratic.
All right.
Okay. This first one we're going to do is, I need to go back to my notes because I might point you to the wrong place. I'm looking at my older version of it. So that's not right. Quadratic 4. Okay. I want everybody to look at quadratic 4. Okay. So let's look at a quadratic 4. Wait. Quadratic 4. In quadratic 4, we're going to do a set of questions. Okay, this is where everything comes together. This is where everything comes together. Okay, all of the things we've done since last week. Okay, so we're going to do all of these and together. We're going to introduce some new concept. But we want to have a thorough understanding of quadratic. That's the goal. Okay, so of course you're given a picture. Of course we're given a picture. And the first we're going to start with the domain. What is a domain, do you think?
All real numbers.
That's right, all real numbers. Because if you think of this function as a rule, any number can be squared and plus 2 times of that input and minus 3, and we're going to get an output. So the domain is all real numbers because for every such input, there's exactly one output, right? So the function definition kicks in. The second question, you may notice that the second question is not about range. Typically, domain and range go together, right?
Yep.
But I didn't ask you for range immediately. I was asking you for concavity. And of course, you see the picture, right? It's concave up. Okay, number 3. Y-intercept. We know that there's always a y-intercept, right? So what is that y-intercept? Y-intercept is where the curve crosses the y-axis. How do we find y-intercept?
You make x 0.
That's right. We set x equals 0. Why setting x equals 0? Why setting x equals 0?
There shows the y-intercept.
That's right, because every point on y-axis, has a common feature. What is that common feature? x equals 0, right? Yes?
Yep.
So when we set x equals 0, this is a 0,
Why
and
repeal
that's
the
0.
system?
So we got -3. Okay? So when input is 0, output is -3, and that is y-intercept. That is y-intercept. Do you guys see that? Do you guys see that process?
Yes.
Okay, because the reason we said x equals 0, I want you guys to understand the reason. Okay, it's very important. Okay, every point on y-axis. Okay, so I'm going to use this to demonstrate because I just want to make sure everybody is here with us. Okay, so I'm going to set up this rectangular system. Oops. Okay, I'm setting up this rectangular system. Six, 4. Okay, just be patient with me. Okay, on this rectangular system, the statement I made was every point, okay, every point on the y-axis, all of these points on y-axis, they have a common feature. What is that common feature? X is 0. X is 0. The
Because it
input is
doesn't move.
0.
Yep.
You guys see that?
Yes, we do.
Very good. I want everybody to see that. So no matter what function you deal with, whether you deal with this quadratic function or you deal with sine function, cosine function, when we ask you for y-intercept, what you do?
Make
You
X
set-
0.
That's right. In the future, you're going to see very complicated functions, but no matter what is the complication, to find y-intercept, what you do?
Make X equals 0.
That's right. And this is the reason why. Okay, every point on the y-axis is what? The x is 0. So the
Oh.
equation for for y-axis is what? What is the equation for y-axis? What is the equation for y-axis?
X is equal to 0.
That's right. So that equation reflects the feature of all the points on y-axis. You see, these are consistent. Do you see that? These are consistent. Hold on. Okay, these are consistent. Okay, so that's question number 3. That's question number 3. Okay, we may not finish all of these questions today, but let's go on. Okay,
Okay.
are you ready? I'm sorry, did someone have a question?
No, I said okay.
Okay, good. If you have any questions, don't hesitate. Okay, number 4. Question number 4. Completing a square. We already did it, right? Completing a square. We already did it, didn't we?
Yes, we did.
We did. What did we get? Can you repeat those steps? Can you repeat that? Can you repeat those steps? right? Adding zero. Adding zero has two purpose to serve, right? One is to make the perfect square, and one is to make sure the equal sign is still valid. Okay, so it serves two purposes. And then we get x minus 1. Oh, x plus 1, sorry, x plus 1 squared minus 4. Okay, now this is where it gets interesting. With that picture, with that form, right? So we basically has an alternative form of quadratic, right? These two are the same. They gave the same picture. Can we graph, excuse me, can we graph this from x squared? Remember all those graphs we did? Can we graph? Even though I give you the graph, I give you the final graph. Can we graph this? Hold on. From x squared. Can we graph this from x squared? Right? So first, we will graph x squared. We know how to graph x squared, don't we?
Yep.
And then what do? We will graph.
You move it.
And we will shift it, right?
Yep.
Shift it where?
Up 3 to the left 2, I think.
To which direction? Up and down, left or right? Right? So this x plus, so we first graph x squared, and then we graph x plus 1 squared. So x plus 1 squared is a kind of, it's a shift. Is it up or is it down? Is it left or is it right?
To the left.
To the left. That's right. X plus 1 squared to the left by how many units?
1.
1 unit. Yep. And then minus 4. So this picture is shifted again. Up or down, left or right?
Down 4.
That's right, down by 4 units. Okay, so this red one is the final curve that you see in the picture. So next, can you identify the vertex? From the movement, can you identify the vertex?
-1, -4.
There you go.
Can you speak louder?
Good job.
-1, -4.
Perfect. Good job. It is indeed a good job. Okay, it is a good job. -1, -4. So from this form, you can see we shifted left by 1 unit and then we shifted down by 4 units. So the 0, 0 is shifted over here, and this point is -1, -4. So vertex, which is the question number 5. -1, -4. -1, -4. Okay, last 2, okay, before the end of the class. Now, can we tell the range? Can we tell the range?
-4 to positive infinity.
That's
you
right.
go.
The range is from what?
-4.
-4
To infinity.
to infinity. Okay, I'm gonna give you an alternative form. I'm sorry, someone is saying something on the chat and I noticed. Let's see, where is it? That's right, Cortland, okay? And I want to give you an alternative form. The alternative form would be, you take the whole thing and you write it as inequality greater than or equals to -4. I know this is something you're not used to, but you need to get used to. Okay? For any real number x. Okay,
Oh, okay.
you got it?
Yep.
So that's the range. We have 1 more minute to go. 7, question number 7. Maximum y value or minimum y value. We know y is for output. We don't have a maximum value because it can be as large as possible, right?
It's infinite. So there's
But
no
do we
max.
have a minimum y value?
Yes, -4.
Perfect. Okay. Y minimum, y value, okay, equals to -4, and this is the minimum y value. Okay, so we end here today, and tomorrow we will continue. You should expect a quiz, and your quiz is about completing make perfect square. Okay, so don't panic. Okay. And I will see you guys tomorrow. Very good job. And I apologize that I don't know what happened to my video. And I'm certainly very happy to see some of your faces, but I'm not able to show mine. And I had a haircut. That's why I'm eager to show you my face.
Oh, okay.
Okay.
Okay, got it.
I know. It's so disappointing. You know?
Yeah, we're all waiting for it.
Oh, right. So I hope you don't get to see me before my hair is too long. And I wish you have a great day and very, very good job. Yes, Mikhail, I can hardly wait to show my new cut, but it doesn't allow me. Have a great day. I'll see you guys tomorrow.
Professor, I
Very
had a
good job.
question.
Very good job. Okay.
Professor, I had a question really quick.
Yes.
So when I was uploading the test, it gave me an issue where it didn't let me upload it to the chat. It said